You'd already pressed record before you did that thing with your hand. What's the unit of power? The power developed by the engine of a car. Okay, stop.
That was too funny.
The power developed by an engine of a car that travels at a constant speed of 32 meters per second on a horizontal road is 20 kilowatts. Calculate the resistance to the motion of the car. So here's the road. Here's the road. Here's the car. I didn't really need a diagram for this bit, but we've got a horizontal road. Don't get mixed up and start doing things about travelling down straight away. It's just horizontal. That's why it says horizontal. So there it is. We've got a driving force driving the car along. We've got a resistance to motion. We have a constant speed. What does the constant speed tell us about acceleration?
0.
It's 0, yes. So we've got an acceleration of 0 at this point. So we need to work some stuff out. We can get this driving force, can't we? Because the power is equal to the driving force times velocity. So that is our 20,000 that we've got there is equal to d times 32, was it? Which gives us a value of the driving force of 625 newtons. Now we're using Newton's second law, using F equals ma, to say that 625 minus the resistance is equal to the mass times 0. So the resistance must also be equal to 625 newtons. There we are. Fairly easy remark to begin with. Now read the question carefully. The car now travels down a straight road. There are at least 3 people who went on to have the car driving up a straight road. But the car travels down a straight road, inclined at 2 degrees to the horizontal. The resistance to motion of the car is unchanged. So we're going to have a new diagram here. Find the power produced by the engine when it's a speed of 32 and is accelerating at 0.1. So I'm exaggerating the slope just to make my diagram a little bit easier. Of course, as soon as we're travelling on a slope, on an inclined plane, we now have to deal with the weight of the car as well, don't we? Because now the weight isn't perpendicular to the motion. So we need to put more on here. We still there would be a normal reaction between the car and the road, but that is perpendicular to the motion, so we don't need to worry about that too much. We have our what I actually call this F, our force down the hill, recognising that that would be different to the force, the driving force that we had in the first part. But the resistance to motion remains unchanged. That's what the question said. And this is the one that we need to not forget about. We've also got the weight of the car. The mass of the car was 1500, so we've got 1500 G there. And we've just drawn this so that this angle is 2 degrees, which means that this angle here is 2 degrees. Slightly exaggerated 2 degrees, but there we go. And so, what can we think about here? Well, if we resolve in the direction of motion, so down the inclined plane, we have F minus 625 plus 1500 G sine 2 is equal to the mass times the acceleration, and the question said the acceleration was 0.1. So we should have that equation. That's not difficult, is it? We should have come straight up with that. We've got to remember the difference between being on a horizontal road and an inclined plane is the weight has an effect on the motion. If we solve this, we get that driving force as being 261.98 newtons. But the question didn't say that. The question said find the power produced by the engine. So we now need to go back and do our power is velocity times that force. So we get the power as being, well, it's 8380 to three significant figures, or 8.38 kilowatts. It's 8383.27 exactly. Interestingly, what they did do with this is they gave a special case of all the marks if you did genuinely misread it and have the car travelling up the slope instead. So if you got the right answer for what would happen if the car was travelling up, which was, I think, 41,200 watts, then you still got the marks for doing that. I think that's right. Yeah, 41.2 kilowatts. Okay.